So we need to learn how to write Lewis structures for covalent compounds. So there's a set of instructions. Write the correct skeletal structure. So you need to get the correct elements and put them down on paper and think about how they might be connected. So this skeletal structure is going to show relative positions of the atoms. And there's some guidelines, but I can't give you a set of rules that's always going to give you the correct answer. Hydrogen atoms are always terminal atoms, atoms on the end. So hydrogen only has one electron. It can only form one bond. So it can't be between two other atoms. It has to be on the end, just bonded to one. Another thing to keep in mind is that molecules tend to be symmetrical. So if you can make it nice and symmetrical, that's probably a good place to start. The second step is to figure out how many valence electrons do I have to use in my Lewis structure. So you look at each of the atoms, find what group they are on the periodic table, and you add those numbers up. If you have an ion, we could draw a Lewis structure for a polyatomic ion. If it's a negative ion, that means it has extra electrons. So a -2 ion, you have to add 2 electrons. If it's a positive ion, you have to subtract electrons. Then you're going to take those dots and spread them around. You're trying to give octets to as many atoms as possible, and a duet for hydrogen. You have to have at least a single bond between atoms so that they'll stick together, right? So start out by making some single bonds and then take the rest of the electrons and try to distribute them so that you can make octets. Sometimes you run out of electrons before you give octets to everyone, and that's when we need to do more sharing, and so you'll need to make double bonds or triple bonds. And you do that by taking a lone pair and moving it to form a double bond. So let's do some examples. Let's write the Lewis structure for carbon monoxide, CO. So the first step is a skeletal structure. Well, this one's pretty easy. There's a carbon and an oxygen. They're going to have to be bonded to each other. They're going to have to be next to each other. So I'm going to put the carbon here and the oxygen over there. And then the next step is to figure out how many valence electrons does this molecule have. Well, how many valence electrons does carbon have? 4. And oxygen? 6. And 4 plus 6 is 10. So I've got 10 valence electrons I can use in this Lewis structure. The first thing I need to do is make a single bond. Bless you. So there's 2 electrons. And then I'm going to take and put lone pairs around and try to get everybody to be happy. So there's 2, 4, 6, 8, 10. That's all the electrons I have. I tend to just, try to spread it around instead of filling up one and then leaving somebody else naked. Is this a good structure? Does everybody have 8 electrons? No, they both have 6. I don't have any more electrons than I can put on there. So now we need to make a double bond. So I'm going to take one of these lone pairs and move it and form a bond instead. So I'm going to take this pair of electrons and I'm going to make a double bond. And I'm going to evaluate. Okay, so did that help? Well, it didn't help this oxygen. This oxygen still has 2, 4, 6. Still not happy. But now this carbon has 8, right? 2, 4, 6, 8. So we're closer, but we still don't have quite enough electrons. So we're going to take another lone pair and share. So which one should I take a lone pair from? Well, I should take a lone pair from the carbon because it has enough, the oxygen doesn't have enough. So I want to take this from here because when I make this into a bond, the carbon still gets to count both of those electrons. So we're going to take that off and make a triple bond. And now is everyone happy? Yeah. The carbon has 2, 4, 6, 8. The oxygen has 2, 4, 6, 8. They both have octets. Sometimes when you're drawing the Lewis structure like that, it may get a little messy, so you can just copy it neatly. I like things to be symmetrical, and so I put my lone pairs on the outsides because I think it looks better, but these are both entirely correct. Any questions? We're not going to care about where the electrons came from. We're just going to take the valence electrons, we're going to pool them. Okay, you brought 4, you brought 6. Okay, we're going to put them in this pot, and then we're going to figure out how we can share them so that everybody can be happy. Let's do another one. Let's do H2CO. So we have to figure out how to connect these. Well, if we went HCO, could that work? No, because this hydrogen would have to be bonded to a hydrogen and a carbon, and hydrogens can't make 2 bonds, they're too small. So that's not going to work. This hydrogen must go somewhere else. So I could put that hydrogen on the carbon, or I could put it on the oxygen. So we'll put it here on this carbon. So we're going to think that these are bonded together and the carbon's bonded to the oxygen, and we'll see how that works. Okay, count up valence electrons. How many valence electrons does hydrogen have? It's not a trick question. Wine. You have to talk louder. So we've got 2 hydrogens that each have 1 electron. How many does carbon have? 4. How many does oxygen have? 6. So 2 plus 4 plus 6, pretty sure that's 12. So we have 12 electrons this time. Start with single bonds to connect everything. 2, 4, 6. And now I'm going to do lone pairs. That was 6. 8, 10, 12. Not enough. What do? I make a double bond. So we should take this pair because the carbon has an octet, right? 2, 4, 6, 8. The other nice thing about this is if you've got dots or lines on all 4 sides, you don't have to count. That one has 8. This one has dots on 2 sides and a line on 1 side. It doesn't have 8. But let's just kind of make a mistake on purpose and see what happens. So I'm going to take this lone pair and share it, and I'm going to look at what I've got. So this oxygen has 2, 4, 6. Well, that's no good. This carbon has 2, 4, 6, 8, 10. It's got too many. So what I need to do is this lone pair is something I can move around. I'm going to put this lone pair over here. Because now I've got 4 bonds for the carbon, 2, 4, 6, 8. And this oxygen has 2, 4, 6, 8, and everybody's got 8, except for hydrogen. Hydrogen's always happy with just a single bond. Easy to please. Any questions? Polyatomic ions, we're going to do the same procedure, but you need to take into account the charge on the ion. It's either gained or lost an electron. So we're going to show the Lewis structure in brackets and put the charge on the outside, unless you're doing a master in chemistry problem. So let's do the cyanide ion. Well, there's only two atoms here, so they must go next to each other. so that one's easy. Then we have to count up valence electrons. So carbon has 4, nitrogen has 5, and then there's a -1 charge. Does that mean I subtract an electron? No, it means I have to add an electron, because electrons are the negative charges, and if this overall has a negative charge, it means it has an extra electron. So I need to add 1. So that's going to give me 10. Then I'm going to draw a bond. I have to connect the atoms. So that's 2, 4, 6, 8, 10. Not everybody's happy. So I'm going to take one of those lone pairs and make a double bond. So I'm going to make a double bond, and I'm going to evaluate. Okay, now nitrogen's happy, 2, 4, 6, 8. And carbon is 2, 4, 6. Not quite. We need to make a triple bond. So nitrogen is the one that has an octet, so I'm going to take one of its lone pairs and share it in here. So now nitrogen has 2, 4, 6, 8, and carbon has 2, 4, 6, 8. They both have 8. And then always a good idea at the end, to make sure that you didn't accidentally add or subtract electrons, count up the pairs. 2, 4, 6, 8, 10. Correct number of electrons. And then to finish it off, because this is a polyatomic ion, I put brackets around it and the charge on the outside. Any questions? Let's do hypochlorite ion. So again, this is a simple one. There's just 2 elements, so chlorine and oxygen. How many valence electrons does chlorine have? 7. And how many does oxygen have? 6. And the -1 charge means add 1 electron. So that's going to give me 14. So now I'm going to distribute the 14. I'm going to start with a bond, so that's 2, 4, 6, 8, 10, 12, 14. I came to the end. I've got the right number of electrons on there, and they all have an octet, and I didn't have to mess around with double or triple bonds. Not quite finished, though, because this has a charge on it. We put brackets around the whole thing and the charge on the outside. Hypochlorite. So the octet rule, if there's a rule, there's got to be some exceptions, right? So sometimes you can't make a good Lewis structure because there's an odd number of electrons. And there's no way that you can do it. So nitrogen monoxide is an example. Nitrogen has 5 valence electrons. Oxygen has 6. 5 plus 6 is 11. It's an odd number. So what do? Well, we just do the best we can. So it's not possible for both of them to have 8, but we can manage to have oxygen with 8 and nitrogen with 7, and that's as close as you can get. Because this is not following the octet rule, we would predict that that molecule might be a bit unstable, that it would be likely to react so that nitrogen could complete its octet, and it does do that. So that's one way that the octet rule is violated. Another one is compounds of boron. So boron is one of the smaller elements. It's element number 5. It tends to form compounds that only have 6 electrons instead of 8 on the boron. So it'll form boron trifluoride, boron trihydride. Those violate the octet rule, and yet that's the Lewis structure for them. And that's because boron's a little guy. So boron does it with less than 8 electrons, and then there are some other larger elements that can go to more than 8 electrons. We call this an expanded octet. Here are 2 examples. Sulfur hexafluoride is a compound, and that's its structure. And here the sulfur has 2, 4, 6, 8, 10, 12 valence electrons around it instead of 8. That's too many. But sulfur does that sometimes. And here's phosphorus pentachloride with the phosphorus having 10 instead of 8. So those happen. We're not going to do any problems like that on an exam, but I just want you to know that exceptions exist. Okay? So there are these exceptions, and yet it's still a very powerful and simple way to understand bonding.